Okay, so the hardy group that's here today. Just to start out, I'm mostly doing this as a front-facing lecture, but I really appreciate questions. I'd much more rather get a lot of questions and run up short on time than sort of go through a whole talk that people aren't interested in. So questions mean that we're going in a direction people are interested in. So please feel comfortable to ask. If something's too much of a tangent, I might just say, let's talk about it afterwards. But I'd rather get interrupted and talk about things that interest people than whatever I have here. So, minimizing noise during fMRI acquisition. First of all, as a starting point, what is noise? I saw this paper last year, which it's a good paper, but I think the most important thing is sort of the title in the first sentence. The title is Impacting the Effect of fMRI Noise Through Hardware and Acquisition Choices, Implications for Controlling False Positive Rates. Sounds interesting. And despite putting the word noise in the title, the first sentence of their paper is, applied to intensity fluctuations of a pixel, the term noise is so nonspecific and carries such negative connotations that it should probably be eliminated from the fMRI vocabulary. And I think this points to exactly sort of the contradiction in both trying to figure out how to give this talk and the contradiction in studying noise. That everyone kind of agrees it's important to discuss noise and what's good signal versus bad signal, but it's really complex to say what noise actually is. And having been in methodology fMRI research for years, I'll say that sort of the most unpleasant debates I've ever been part of aren't whether how to remove noise. It's two people who think different types of noise are more significant for their analysis arguing over whether they're right. So one person saying, I think removing head motion noise is the highest priority, and someone else saying, no, I think removing artificial biases in your analyses is the type of noise that's most significant. And all too often in these debates, people kind of talk past each other as opposed to actually, saying, okay, these are different priorities that we're discussing in that way. So it's kind of, and so getting on the same page of sort of what is noise and understanding that noise is both an extremely messy and important term is key here. So after that, what causes noise in MRI data? So maybe I'll give some chance if people want to throw things out. We'll see if we kind of do my whole talk as a people guessing it right now. But what do people think are the issues of noise with MRI data? Excellent. It's going to be that type of room today. By the way, a bunch of other people came in, so I'll say the same thing again. If you want to be passive, that's great. But if you have questions or something's confusing, please ask. I'm much happier answering things that people have questions about than finishing this talk. So I'm dividing noise here into a few different categories. I would call one is measurement errors, such as sort of noise based on how the MRI machine can or cannot record the data, which is sometimes called thermal noise, or undersampled data. And undersampled can be a technical term, but it essentially means you're collecting data and you're not able to collect all the information that you would like. So that could be you're recording, you're interested in recording heart rate, but you're not sampling heart rate fast enough, or it could be that you want to sample an entire area of, in the MRI volume, it's called case space, but you're not sampling at as high a resolution as you would like. So I kind of consider both of those undersampled. We can have imperfect data processing. So there are assumptions in how we reconstruct data. I think that this is true with all MRI. I think it's particularly true when we do acceleration, which means you essentially undersample your data acquisition and then you use reconstruction magic to figure out what you missed. Yes?
So when you say imperfect data processing, you mean if there was some perfect algorithm for reconstructing, then this source of noise would not be there?
If there's a theoretical perfect way to reconstruct something, you would still have undersampling. So let's say you do acceleration and you collect 1/10 of your data and you have, you say based on this math, we should be able to reconstruct it back. You'll still have sort of the noise from the undersampling, but theoretically there could be a way, if you could model everything, to get rid of artifacts and other things caused by the reconstruction flaws. And the last is imperfect signal modeling. So that could be not acquiring information that would be useful to account for noise that you want to remove, or even something simple as bad alignment between images. Like you don't either from distortions or post-processing algorithm, you don't have things lined up the way you want. So the whole talks about minimizing noise, but what do we mean by minimizing noise? And I'll come back to some of the stuff in more detail, but I realize there's a bit of vocabulary that I want to make sure everyone has sort of a general awareness of what the vocabulary is. So when we're talking about minimizing noise, often that could be maximizing the signal-to-noise ratio, or SNR. And if you've been to some of these talks, I'm sure people throw the phrase SNR around here all the time. And hopefully some of them define it, but maybe not. So SNR is essentially the quality of the signal you have versus the quality of where you don't want signal. So in this case, you can see we have a nice, everything's relative. So high and low is relative, but here we have a high brain image and kind of very dark in the background. But a low SNR would kind of have more garbage both in the data and in the background. So, and this is sort of, I actually artificially made this image, but this is always something that happens in MRI images, that there's always some conflict between what's your signal quality in the volume you're measuring versus the signal quality in the background. Interestingly, SNR is important, but it's secondary for fMRI, I'd say. So temporal signal noise is often much more important, which is the best example of what temporal signal noise is if you put a bowl of oil, often called a phantom, in the scanner, and you collect an fMRI time series on that, you don't want to see the signal changing. Because if there's nothing changing at all, it's just a jar of oil, there's no brain function, there's no anything, you want a flat signal. So temporal signal noise classically would be essentially the mean, you take a time series point, you take the mean of that, and you divide it by the standard deviation of that, and the bigger the mean over that standard deviation, the higher the temporal signal noise is, which means your signal is really big and the amount it's fluctuating around that signal is really small. And as you can see from this example, it's never infinite, because there's always, based on thermal noise and estimation errors, there's always going to be some fluctuations that you don't want to see. And this colored image is actually the temporal signal noise, this mean divided by standard deviation mapped on a color map. So you can see, even in this jar of oil, there's different areas that have higher and lower temporal signal noise. And the reason that's of interest for fMRI is because when we're looking at a time series, we don't really care if, your signal is 10,000 versus background noise of 5. We care that if you're taking a time series, it's as stable as you can, and any fluctuations you see actually relate to fluctuations in the brain. And the third terminology that's often used with this, which is probably the most interesting and sometimes tricky to measure in fMRI, sometimes tricky to actually estimate, is contrast to noise, which is you do some sort of task. So in this case, someone was showed a flashing checkerboard for 20 seconds, and this is the response in the Calgren sulcus, and you can see the response goes up when the checkerboard is appearing, and then down and returns to baseline. But if I collect the same task 100 times, you can see that the gray background is sort of that variation it shows. So sometimes the response is a little bit bigger, sometimes a little bit smaller, it's a little bit noisier. So contrast to noise, one way of measuring it is essentially the response change, the magnitude of the response change you want to see versus sort of the unmodeled variation that doesn't fit your model. And that's tricky to measure because to make a precise measurement, you actually have to have a model of what you expect to see. The other way contrast to noise is used in MRI is if you're looking at a tissue picture, you can see the difference between different colors of contrast. So like here's gray matter and white matter, and you can see that there's a very clear boundary between these two tissue types. And in the noisier images, it's not quite clear. So often in MRI images, that's another way contrast to noise is used. So it's either contrast between different tissue compartments or contrast in a response in fMRI. So continuing what we mean by minimizing noise, we can talk about minimizing specific artifacts. So like Charles was saying earlier, a lot of these are dealing with reconstruction issues, but some of these are also dealing with noise in the input signal. So like, for example, this first one is caused by a specific frequency of noise that's being recorded in the scanner, and the specific frequency of noise is causing these zigzag stripes across the entire image. Then you can have what's called Nyquist ghosting, which can be solved with a mix between the pulse sequence you decide to use, your reconstruction method, and essentially the scanner hardware. And this one over here is sort of a really bad artifact based on acceleration misreconstruction. So I'm not going to go into the specifics of all these artifacts. I can leave that for one of the more physicsy lectures. But the basic idea, and these are all three very extreme cases, but you'll see them. If you're looking at enough data, you will see all three of these in data. And when we're talking about minimizing noise, these are very often the ones that give us the most headaches, because if you're not careful and you don't notice them, these are the ones that are going to not only add random noise, but actually bias your results. For example, as an extreme case, let's say I'm imaging the brain area back here, and I don't notice this Nyquist ghost because it's just a little bit dimmer. I might be getting my brain response up here too, because essentially what this ghost is this is called a ghost because it kind of looks like the shadow of the actual thing you want to see, and the back of the brain is essentially looped over to the front of the brain. So you'd get like maybe 1/10 of the signal up here, and you'd say, hey, I'm getting a big response in the back of my brain and a weak response in my front of my brain, but it's actually completely artifactual. And if you don't look for it, you might be revising all neuroscience knowledge. The other thing, which a lot of people who spend a lot of time with fMRI is the bane of their existence, is you want to minimize distortions and signal dropout. Particularly for fMRI, such as echoplanar, with things like echoplanar imaging, we were trying to collect, or anything we were trying to collect the volume of data as fast as possible so that we can keep collecting one volume after the other every 1 to 2 seconds. In some way, you're most likely going to be exciting the protons once and then trying to collect as much data as you can afterwards. And those methods in general cause distortions of the brain shape, and they cause dropout. And depending where you're trying to look at in the brain, these can cause you a lot of headaches. I'll also add, it's gotten better, but I'd say the first generation of fMRI data, there was a bunch of people who were publishing work saying they saw weird results in the orbital frontal cortex, which is like right above your sinus, like right under your nose. Or they're saying, we expected to see it in this condition and we didn't, therefore we think there's something, we've discovered something new about the brain. And then people who actually knew how to look at MRI images said, you look at your raw data, and they go, no, why would we look at our raw data? And they look at the raw data, and the orbital frontal cortex was a big hole in the front of the brain because that entire area was dropped out. So there's, if you're bored enough to look through some of the earlier papers, there's a whole bunch of stuff where there's discussions of orbital frontal activation that essentially was dropped out brain. Also with minimizing noise, we can talk about minimizing head movement, breathing, respiration, chest movement. The one that often gets overlooked in this discussion is unmodeled behavior and neural activity, which is, people come to this lecture probably thinking about MRI and MRI physics, but if you tell someone to do a task and they don't do it, that's noise in your data. Or if you tell someone to rest in the scanner and one person is spending the whole time doing meditative breathing, and the other person is spending the whole time thinking about their grocery list later that day, that's unmodeled noise because you had no idea that was happening. And lastly, there's unmodeled noise in sort of how the response looks. So things like how the blood oxygenation changes we typically measure with fMRI relate to actual neural activity. And there's some of that we can model, some of that we can't, but that also adds noise to the data. the last sort of group in this intro area is, we can either improve temporal resolution. So what this is showing is the red line is what's called a power spectrum plot of bold data with a fairly typical sampling rate. And you can see we're getting a big response at like 0.01 hertz. And that response drops and drops and drops until like 0.15 hertz. But if you collect data with a higher temporal resolution, so these blue and green lines are sampling every 700 milliseconds, you see that you have another peak over here. And what this is the cardiac and respiration responses, which are a little bit faster. And by sampling that, we can actually remove that pretty easily. If we didn't sample that, it kind of folds over and it's less mild noise. So some people like high sampling so they can more directly remove that. And the other method is by improving spatial specificity. So this is an example of, I'm assuming this is M1, where if you get high enough resolution, you can actually look at different layers within a cortical area. And if the voxels are bigger, there'd be no way to look at this thing. So this is the cortical layer here is about 3 millimeters thick. So if you want to get sample cortical layers, you have to get voxels that are small enough to actually distinguish things, and then you can actually do neuroscience on layer-specific cortex. So this is the big list I've kind of done so far. Different ways we can minimize noise. And the rest of this talk, I'm going to give examples on this. But I think the big take-home message so far is, when we say we want great data, we want everything. We want high resolution. We want high temporal resolution. We want responses that can be resolved, that the contrast noise is so big that just a few trials give us the data we want. And we want no distortion, no dropouts, no artifacts. But the reality is that's impossible. There's no sequence nowadays that kind of gives us everything. So when you're designing a study or you're evaluating a study that you're reading in literature, everything is a balance of priorities. There's no real definitive right answer, although the bad part is there's 100 ways to do things wrong. So if there's anything you're taking from this talk, it's just to sort of start thinking about these issues and learning to evaluate what you care about and prioritize. Just as a very basic example of that, a lot of people, when they get to the scanner for their first own study, they're saying, what pulse sequence do you use? Or what parameters? And they go, oh, I use the parameters of the person that someone else gave me from before. So, I was using 3 millimeter voxels, 2-second TR, whatever. And that might be right, but it could be that you're studying something different, and for your priorities, you really should have rethought about that and tried to examine, done something slightly different. So it's useful to be conscious of why we make these choices so you can make them better in different situations. So that's kind of an extended introduction. I'm going to go into a bunch of examples now. I'm dividing these examples in 3 areas. One is kind of the MRI physics part, parameters and pulse sequences. And then parts, dividing some of these into peripherals and participants, and preventative scanner health, I'll call it. Before I do that, does anyone have any questions? Yes?
Why is SNR calculated as like comparing the tissue to non-tissue, I guess? Because it seems like comparing it to this volume that's outside of the the region that you're imaging is not necessarily comparing it to a baseline, because there still is, there's air there that you may have, there's air conditioning coming from one end of the scanner and not the other.
Yeah.
I guess bias is inherent to that.
So the question is, why do you, but I'll try and repeat questions when I remember, because this is being recorded for all eternity. So the question is, why do we calculate SNR as sort of within the brain tissue versus outside versus other things? And the quick answer is we don't always do that. The SNR is essentially an equation for signal divided by noise, and there's judgment calls on how we define signal and how we define noise depending on what we're measuring. So for example, when we do sequences with some sort of acceleration, they fit the data to a model. And what that means is outside the brain isn't actually just sort of random junk outside the brain. It's sort of the artifact of that model fit. So in some sequences, what's outside the brain can look very, very weird and not really represent your baseline noise. In those cases, what's ideal is you actually have your tissue, whatever your sample is that you want to measure, either a phantom or tissue. You collect an image of what you want to see, and then you can actually collect another data set with pretty much all gradients turned off, or not necessarily gradients, all. I'm blanking on the term, but it's essentially you shut off everything that gives structure to your image, so you're not actually exciting your tissue sample, and then you collect an image that's essentially a no data image, and that just gives you the background noise, and then you can essentially divide one versus the other. And I just gave you the hand wave version. Depending on your sequence and depending on what you do, some interesting things can happen. Like the sequences that require sort of a calibration scan, if you mess with that calibration scan, it could make that background noise image even more garbage, or even worse, it could take a garbage image and create something that isn't there. So in practice, SNR can get interesting to calculate, and there's a lot of stuff you can look into on that.
Was
Yes?
there a plethora of P's on purpose?
Probably. The question was the plethora of P's on purpose? Yes, probably. I was bored. Or more specifically, I think I had half of them P's, and I figured I'd work the rest of the way. So parameters and pulse sequences. First, I'm going to go through a bunch of examples here. The first thing I'll say is this is a semi-arbitrary list of examples. This is not sort of an all-encompassing lecture on what matters for MRI acquisition for one major reason, which is talking about everything that matters with noise and fMRI acquisition is essentially a entire course on MRI physics, which you probably wouldn't have me give, first of all, and second of all, is more than we want to cover in another half hour or less. So what I'm going to try and go through here is a bunch of examples how noise varies and ways to think about noise that'll hopefully get everyone here thinking about if you're looking at your data or planning a study, what to think about and what questions to ask. It won't give you sort of the answers of every thing to make up noise, but it'll hopefully at least give you the questions that you know what to look for. So general acquisition goals. You want to, I've mentioned this a little bit already. You want to give a thought to the priorities of your study. Do you really want to get sensitivity? That means I really want to see what's active, what's not active. Or do you want to get specificity, which would mean I really want to know if this activation is in the anterior amygdala versus the posterior amygdala, or I want to see if this is in motor cortex layer 1 versus layer 5. So those are different priorities, and you're going to choose different parameters for those. Do you want anatomical accuracy, as in like is distortion something that you really, really don't want? Do you want to get robust against, general artifacts, or do you want to be robust against specific artifacts? For example, there's been a bunch of studies showing how motion, if you're doing a population study and you have two populations like children and adults, where motion varies, and you want to find, head motion varies, kids move their heads more, believe it or not. And you want to do a comparison, then you're going to be very concerned about choosing stuff that will minimize that head motion, because that would give you a source of noise that's going to mess up with your whole study. And I'll also add that the optimal acquisition options aren't always obvious. And I'm going to start with one that's possibly the most boring parameter you could think about, but it's a good example of how something that no one thinks about does or doesn't matter, which is what's the best flip angle for an fMRI study. So a flip angle, I'm not sure, this is probably covered in one of the earlier lectures, is you have something in the scanner, and the first thing you want to do is excite the protons, because then the protons coming back to the baseline is what our signal is. So the flip angle is essentially how much you excite those protons. If you want to sort of put it in the classical physics model, a 90-degree flip angle is you excite the protons. Essentially, your protons are facing along your steady state axis, and 90 degrees means you knock them 90 degrees off the steady state axis, and then they return to baseline. A 45-degree angle is you knock them off just 45 degrees off axis. So if you look at this data, depending how much, this red curve is signal to noise. So there's an optimal flip angle, classically called the Ernst angle, where if you knock your proton, given various parameters, if you knock your protons off that axis, that's going to be the maximum signal change that you get. And what you can see is as you move away from that optimal flip angle, the signal to noise decreases in kind of a very sharp response. So if you're caring about SNR, you really want to sort of get as close to that optimal flip angle as possible. But if you care about TSNR, this temporal signal noise, which is what we often do in fMRI, you can see TSNR, sort of one way of writing it, has SNR on the top and the bottom, times this lambda squared, which is a measure of physiological noise. And you can read more about it in this paper down here if you want to know more about that method. But the basic idea is if you have a decent amount of this physiological noise, that's things like blood flow and tissue response and other stuff, then you actually don't get this huge shape, you get a much flatter shape. And there's a huge range when your flip angle essentially doesn't matter. And what that means is if you look at, you have a flash and checkerboard task, you're looking at the visual cortex, and if you look at sort of the raw response change, you can see that optimal flip angle is going to give you the biggest raw signal change. And the further away you get from that optimal flip angle, your response is going to get smaller and smaller and smaller. But if you kind of scale these all to the same maximum minimum, what you can see is all your responses, if you see like sort of how much they squiggle around that shape, look almost identical. So it's essentially, for a wide range of flip angles, it's the equivalent of like multiplying your data by 5 or 10 or 15, but the actual response and the actual noise in that response is almost identical. So that means that if you're designing a study, flip angle is a parameter that doesn't seem to matter as much as people thought for a long time. And just for background, the reason people care about this is if you have a low flip angle, you're heating the brain less, which is relevant for some sequences that are kind of pushing the limits of what we can do. You're also getting less what's called inflow, because if you're exciting them less, then when you excite protons and blood pushes those protons somewhere else, they'll return to baseline sooner. And you also get a bit better gray-white contrast in your fMRI data, which is useful if you want to do registration. So there's reasons you might want to sort of push away from that maximum flip angle. And it turns out it doesn't matter as much. Other parameters, when we're talking about voxel size, traditionally we kind of say that smaller is more challenging because you have lower signal to noise. Just to give you an example of this, whatever you're measuring is based on the volume you measure. So the more you're measuring, the better signal you have. So if you have 3 by 3 by 3 millimeter voxels, which is fairly standard for like a 3 Tesla MRI, each voxel contains 27 cubic millimeters. But if you're using 1 by 1 by 1 millimeter voxels, which doesn't feel that much smaller, it's just 2 millimeters smaller per voxel. But if you're looking at the actual volume, that's 1 cubic millimeter. So you're getting essentially, every voxel has 1/27th of the tissue measured, which is a huge hit in your signal to noise. So if you want to image at 1 millimeter, you have to sort of push a lot of other limits or go to 7 Tesla or do a lot of other things to sort of get good enough data quality to collect images. And the other thing is, like, even if 1 millimeter is a lot lower SNR, if you're averaging over fewer things that matter, you get better data. So this is, again, this example of layer-specific MRI, that if my voxels were 3 by 3 by 3, then they'd be covering this entire area, and this really neuroscientifically interesting pattern of seeing an effect that just hits the higher and lower layer separately would be gone. But by getting a more spatially specific response, you're not averaging. You're only looking at things that have the signal response, and you're not sort of averaging between tissue that isn't interesting. So depending on what you're doing, you might say, I want to get that high resolution. I want to look at something really fine resolution, and the sacrifice in signal to noise is worth it. Or you might be saying, I don't care about things that are 1 millimeter, and I want to get as much as I can with less data. Yes?
But is it true that if you did the 3 by 3 by 3, it would be equivalent to doing the 1 by 1 by 1 and then averaging those 27, or is there a slight difference?
There can be differences. So in some cases that could be true. In other cases, let's say you have an area with dropout. So if you had a voxel that included some areas that are clean tissue and some areas where you're sort of getting dropouts or other distortion, by combining that together, you're messing up that whole area. But while if you're doing it separately, you would get much more spatial specificity. That's just one example of where it could matter. If all other things being equal, collecting 27 small voxels versus one big voxel could be equivalent, but all things are almost never equal. And dropout is just kind of one example of that. So with TR, generally, the shorter your TR, you're taking a little bit of hit to signal to noise, but possibly you're getting better temporal resolution, which could possibly mean a higher temporal signal to noise. You can potentially, short is also good because potentially you can just directly filter out these high frequency artifacts. I showed this before with breathing respiration. But there's a lot of people now pushing your TR as short as possible because they think that's, this high resolution stuff and directly filtering these artifacts is the best. But push comes to shove, when we're measuring fMRI, we're still limited by hemodynamics. So this is, my 20-second response, and you can see even after the 20-second response ends, there's a huge slow return to baseline because blood flow is not neural activity, so it's a bit slower. So as long as we're limited by, if the effects we're interested in are relatively slow, then sacrificing SNR and TSNR and adding artifacts to sort of push your TR as short as possible, just because sometimes bites people back, for lack of a better way of saying it. And the last one, which I've sort of half covered, is acceleration methods. So this means collecting only part of K-space and either collecting multiple slices at the same time or collecting, using a 3D accelerated sequence, so you're collecting only part of the whole volume, or collecting within slices partially. And depending which method you choose, you're sometimes taking a direct hit to your SNR to do acceleration, but it makes things like those shorter TRs, smaller voxels, and things like multi-echo fMRI, which I think there's going to be a whole lecture on later, practical. Doing things faster also potentially reduces dropout and distortion. So you might be taking an SNR hit, but suddenly you have your orbital frontal cortex back. But the problem in all these methods is whenever you're doing acceleration, if your reconstruction is not perfect, either because the calibration information you collected was not perfect or your algorithm to reconstruct is not perfect, you sometimes get artifacts that you'd rather not get. So now I'm going to go through a whole bunch of examples, and time willing, I might go faster or slower, just to give you a sense of what they look like. So this is an example of these images I got from Lanchas Huber over here. I'll be going through a few of your examples here. This is just an example of, what's it called again? What I was just saying, if your calibration scan is flawed. So a common type of calibration for in-slice acceleration is you start by collecting this EPI calibration scan, which means for every excitation pulse, you're collecting a few lines of K-space, and that's fast, but it also makes a little bit more distortion than you'd like. And that's, if you use this EPI calibration scan and then you reconstruct, one data set, let's say this is how it looks like. If you use a different calibration scan, which is exciting, per line, so it's going to be a bit cleaner reconstruction data, even if the actual data you're collecting is the same, if you're using the cleaner reconstruction data scan, you can see one of these images looks a whole lot cleaner than the other. You can also see things like this out of brain artifact over here. So purely changing that calibration scan and not anything else can make a big difference in this one example. And it's also just another thing to point out in general. When you're looking at your data, if you're seeing things like big blobs of signal outside before you do any reconstruction, any processing, if you're seeing big blobs of signal outside the brain that look structured, that's the sign that you might want to look at things a bit more carefully. Here's another example of something people don't directly think about often, which is fat ghosts, which are caused by chemical shift. I'm not going to talk much about that here, but chemical shift and fat ghost is sort of the thing to search for if you want to look into this more. Here is a volume from a vasoscan. And if you look carefully, you might see a little color change there. But if you then take the standard deviation of this image, you see, so this is a time series, and if you take the standard deviation, you see this big bright line here. And what that is in certain MRI sequences, the fat has a different excitation frequency than water. So we're aiming to measure water, and what that means is we're exciting fat at a slightly different frequency than water, because fat excites at a different frequency. And that essentially what that means is that if your fat creates signal, the fat is going to appear in the brain. It's going to appear in the image at a different place than it otherwise should. So what you're getting is the fat that would probably be like skin or marrow up here is, instead of appearing out of the brain, is going to be shifted back into the brain. And what we usually address that with is in sequences where this matters, that you essentially saturate the fat signal, and then when you collect the signal of interest, you've removed fat, and then you're not going to get fat where you don't want to. And you can see here, if you're doing a really strong fat saturation, you don't get that artifact. This is an artifact that was pretty significant for some volume vasoimaging, cerebral volume vasoimaging Renzo was helping me with. But it's also a huge issue for diffusion imaging, because especially if you're trying to do tractography. So people doing diffusion imaging are very often either talking about or very thankful that they're using an aggressive fat saturation. Another example is sort of how motion affects data. And I'll say this is also vaso, which many people, which only a few people are currently using here, but hopefully many others will. And what we're doing is we're collecting two slices simultaneously in this volume. And what that means is, that those first two slices, you see the two things are coming in parallel. Everything appearing in parallel is being collected at the same moment in time. And you can see there's this border where things are being collected about a half second apart. And it makes that little bit of a line, which doesn't seem like that huge a deal. But then if you add head motion to this, as it's moving through the head motion, that line in the middle, you're merging data that's being collected a half second apart altogether. And that means that even after head motion correction, instead of having the straight line, you're getting the boundary line moving around depending on where head motion is. And you can see, if you look at a time series right on that border, so where that red line is, the image kind of has brightness and darkness. And if I wanted to do a fMRI contrast in my task, I see this big, beautiful positive activation in the back of the brain and big, beautiful negative activation at the front of the brain. That's an artifact. It's an artifact of looking right around that boundary. If we use a different reconstruction, which is called 3D EPI, you're sort of filling in the entire 3 dimensions of K-space over several excitations, which sometimes has its own issues, but it doesn't have sort of this edge discontinuity you see in the 2D image. And in that case, there's no edge discontinuity with motion. There's no edge discontinuity when you correct for motion. You don't see the brightness change. And if you want to do your activation map, you see a much more focal activity. In this case, this was a breath holding study. So the actual goal of it, so you actually do expect to see a global signal change, primarily in large vessels. So that's exactly what we're seeing here. And again, to sort of drive home the point I've driven home several times here, which is the best depends on what you're doing, and it varies on a lot of stuff. So for example, that I was just showing you how great 3D API is, but it turns out it varies based on what you're imaging. So if you're imaging in the classic range of like the classic 3T range of 3 millimeter cubic voxels, you can see that the temporal signal to noise ratio for the 2D EPI is actually a lot higher than 3D EPI. Oops, wrong way. If you want to image a little bit smaller, then what you're seeing is the temporal signal to noise is a little bit closer. And if you want to image at this really low, like 0.7 millimeter voxels, which are good for this layer-specific stuff, your 3D, you can see sort of here, we get a nice robust signal across the entire sensory motor cortex, while if you're at the 2D, it's kind of just much more noisy and sprinkly. So you can see that depending on your resolution, depends on whether or not you might want to consider a 3D sequence versus a 2D sequence. Another thing to think about is a lot of different sequences are sensitive to different areas. So some sequences are much more sensitive to small vessels versus large veins versus large arteries. So for example, gradient echo bold is, so you see like a big blue thing here, is heavily sensitive to large veins, and it has some sensitivity to, you can see sort of, if you follow this line, it's how much blue versus red versus green is on it. So it's very sensitive to large veins and partially sensitive to large arteries and small vessels. If you take something like a diffusion-weighted sequence, you can see it's extremely sensitive to small vessels and sensitive to almost nothing else. So just looking at this picture, I would say, yeah, we should all be using diffusion-weighted T2 prep sequences if we really want to get these really high-resolution stuff. But the thing that isn't shown in this figure is your signal noise and temporal signal noise. So some of these sequences, so the power of gradient echo bold is you're essentially wasting none of your signal to noise, so it gets really large responses, while something like a diffusion weighted sequence is going to be much more is going to spend a lot more SNR getting that specificity. So just an example of how these different images look. Here's the pulse sequences for a bunch of these. Here's how the contrasts look. So I'm not going to go into this in too much depth here, but you can see that each of the images has quite a different contrast. If you look at the functional responses, you could see, so gradient echo bold, you could see has one of the most robust responses. So it's a big, bright, this whole huge area is bright, strong activation, but you'll also notice that it's not very specific. So it's going the black area you can see here is the cerebral spinal fluid, which often has large veins in it. So the gradient echo bold has all that signal there, and it's blurry. You don't see that much specificity. But if you go to something like vaso, you're still getting a fairly robust response, but it's really staying within the tissue. If you go to some of these that are much more sensitive to tissue, you might be getting that specificity you want, but you're just losing signal because they cost a lot. So if you want to look at this as sort of a comparison of sensitivity, which is how likely, how much signal you're going to get and how likely you're to get it, versus specificity, which is how precise are you going to image, you can sort of make a scatter plot where gradient echo bold is the one that's going to sort of, if there's activity to be found, it's going to find it. And diffusion T2 prep, diffusion-weighted T2 prep is you're going to take a lot of data to get any signal because it's very low sensitivity. But if you collect enough data to do it, it's going to give you pretty good specificity. And the reason Ranches Huber likes this slide is because vaso, one of his favorite methods, is a really nice compromise where you're getting not quite the sensitivity of gradient echo bold, but you're getting nearly as much specificity as the best of the other methods. So as you're thinking of methods, this is sort of the way you can decide those compromises. This is an anatomical example, which is just showing that if you want, there are real-time motion correction for functional MRI, but it's kind of easy to visualize with anatomical. If, while you're collecting, the person's head moves to this anatomical image, you get all these kind of ringing in it. But if you're sort of correcting for that during acquisition, you get a much cleaner image. So things like real-time motion correction are relevant. The other thing to think about is calibration or baseline scans. So if you're, let's say, doing a population study, so in this case, I was studying a younger population versus an older population. And I had these hemodynamic responses in 4 different brain areas. And I was able to see that in young volunteers, the volunteers had bigger responses than in older volunteers. So is that neural? Are older people getting less signal response, or is this something related to vasculature changes? So what I did in this case is I used a hypercapnia task, which is you increase CO2. In this case, I told people to hold their breath, and I saw what is the response when they hold their breath. So that, in theory, is not going to be heavily weighted by neural variation, but it's going to be heavily weighted by vascular variation. And what you can see is in some areas that vascular variation is appearing in the older patients, but not quite as much as not quite as big as here. And if I essentially divide these two, you can see that I'm still getting a signal drop with aging. Can I definitively say that people who are older are getting less neural activity? No, because everything is relative and everything's complex. But this gives me one more bit of confidence that what I'm looking at is neural versus just a vascular artifact. And there's a lot of stuff on this calibration literature. I'm not going to go into too deeply, but I wanted to make sure everyone is sort of aware it exists. My second double P category. Any questions before I switch into this next section? Okay. So this is kind of the category. I wanted to start with the pulse sequences because that's what people most think about. But I feel like this is the category that most people ignore to their detriment, which is why I definitely wanted to cover it here. So if there's any take-home message for the regular imagers here, I think it's that you want to collect respiration and pulse data. So very often when this discussion happens, people talk about actively removing signal. So there's these methods with fancy acronyms, RetroICOR, RVT, all this stuff on sort of how to take these respiration and pulse signals and regress it from your data. For various reasons, people don't bother to do that stuff. And they say, well, if I'm not going to do that, it's not worth collecting this data because it's just one more thing to put on people. My take-home message is collect the data anyway. This is the first example of why. Knowing what your volunteer is doing is essential. So this was a block design task where people say, so a bunch of letters, is it a word, not a word? This is their breathing depth changing over time. So what you can see is while they were performing the task, they were breathing deeper than when they weren't performing the task. And if this was a population study comparing 2 populations and one subject breathed deeper than the others, you would really want to know that. And you would want to think hard about how you're going to handle that in analysis. If you didn't collect that data, then you can, live in blissful ignorance. And just to make it sort of a little bit more personal, this is a minor confession from one of my studies. This is the same study I was showing with respiration, with the breath holding calibration earlier. In the task, the published paper, I was putting this flickering checkerboard. It appeared for 200 milliseconds, and it appeared every 18 to 24 seconds. Whenever it appeared, people moved their eyes and pressed a button. I got these beautiful responses. Great study. That was published. Now there's the part of the study I didn't publish. I was also interested in hemodynamic variation over different durations. So, how does the response change between young and old if you're presenting a stimulus for 3 seconds, 6 seconds, 12 seconds? There's a bit of a literature in this, and I was curious about how it affected with aging. The trouble is I was collecting respiration and cardiac signal, and it turned out that a non-trivial number of my volunteers just held their breath whenever the checkerboard appeared. And like I said, a breath hold is like a really potent global response to your blood signal. So your whole brain becomes, your whole brain gets more blood flow when you hold your breath. So pretty much that made the data unusable. And the big thing to keep in mind here is if I hadn't collected that data, I would have seen these beautiful responses in my nice prescribed regions of interest and said, this is exactly what's happening here, and I tell a story and I published it. But because I saw these huge breath-holding variations in my task, I deemed that data unpublishable. It was an artifact that I couldn't account for and couldn't correct for, and it wasn't, there was no sign. I mean, I guess I could publish on, here's an interesting artifact, but there was no legitimate way to publish a scientific claim based on that data. And the thing that was going through my mind when I originally made this slide was, how many studies with variable response durations didn't collect respiratory traces and have the exact same thing happening? So my take-home message, if you're collecting data, please, please, please collect those respiration and cardiac traces, because, I don't know, maybe if you want to publish bad data, you can do it, but if you want to see like artifacts in your data and decide that you're damaging science by publishing bad findings, then, go ahead. But it's really important to collect it to know when these things are and aren't happening. Given the time, I have one more example using spin labeling. Same take-home message, which is collect. These slides are all going to be available online, and you can hear me if you want to actually look at those pictures later, and I can talk to you. Basic advice for collecting respiration and cardiac data is make sure your respiration and cardiac traces are actually synced to your acquisition times if you're going to use it for anything. A very, very large multi-million-dollar study was told they had to collect respiration and cardiac data, and they did so, and they didn't really pay attention. And then they came to us several years later saying, it's not synchronized with our scan times. How exactly do we synchronize this? Don't do that. So, if you're starting to study, make sure you have some way to make sure they're synchronized. For respiration, just so the people who are actually doing this, there are some respiration belts that auto-calibrate over time, which means you actually can't get a reliable volume trace over time. So be aware if you're using one of those or not. I think that the default Siemens settings are that way. They auto-calibrate. And for pulse oximeters, they can be very sensitive to finger movement. Take time to make sure it's secure, and it won't. So the way I tend to do this is I put the pulse oximeter on the finger, I wrap some stretchy tape around the finger and around the wrist so the wire doesn't yank, and that seems to work really, really well on our pulse oximeters. And monitor the traces during the scan. If they look bad, correct it then, not worry about what happens later. Other thing to keep in mind is, you can monitor things like eye tracking. So a lot of people monitor eye tracking for things like, stimuli that you care where people look. But Katie Chang, who works here with Jeff Dunn, had a nice, elegant study, which just said, if you say, are people's eyes open or closed, what does it look like? And you could see, actually this is eye arousal, so I guess it's pupil dilation. And you can see that you're getting a correlation just based on the arousal of the eyes. So if you're going through the effort to collect eye tracking, which is non-trivial, you can model some noise variation that you wouldn't have otherwise modeled. Head movement is the bane of a lot of fMRI studies' existence, but some people don't, a bit of effort spent at the beginning to reduce head movement is huge. Sometimes it could be as simple as checking, explaining why you don't want head movement to the subjects and making sure they're extra comfortable. But in general, don't assume that sort of like someone showed you this is how you restrict head movement the best way. It varies by your receiver coils. It varies by your patient population. There's all sorts of stuff that varies, so it's worth, for any given study really trying to reduce head movement. And there's more and more options to reduce head movement. Here are some, we've been using these inflatable pads a bit. There's other people who are making these sort of custom fit foam heads, which work really nicely, I've been told. But these are just two examples. So if you really if head motion is really a matter to you, instead of trying to work with it in post-processing, it's worth giving serious thought to how to fix it at the acquisition point. And yeah, just prepare your participants. Making sure they're comfortable at the beginning is surprisingly ignored and surprisingly important. And the last point I'm going to this next slide is noise is not independent from task design. So here's a study that essentially said, how much do people's heads move? So these are the same population doing a bunch of different tasks based on, whether they're doing rest at the left versus tasks that sort of involve more and more cognitive activity. And what you can see is in the control population, ADHD, bipolar, and schizophrenia, the more engagement they have, the less their head moves in the scanner. This is another study that essentially showed the same thing, that there's a lot more motion in kids and adults in rest versus watching a movie versus watching a glorified screensaver. So with very important properties. Sorry, the person who helped work and I just walked in the room. Yes. Glorified screensaver. Can I say that? Okay, excellent. I've gotten approval to call Inkscapes a glorified screensaver. Now, the take-home from both of these is there's a lot of people talking about resting state fMRI, but, and there's also a lot of people doing resting state fMRI saying, oh no, head motion is a huge problem, and head motion is our biggest problem. But if it turns out putting a low engagement visual stimulation on the screen that's, just not supposed to evoke anything, suddenly reduces your head movement, maybe we shouldn't be doing straight resting state scans, and we should be giving people enough engagement that they keep their head still. The last section, which I'll cover in the last few minutes, is preventative scanner health, which is sort of my way of saying, and here we're very lucky in that we have a staff that takes care of this, but there's other things that you can do here or elsewhere to sort of learn to pay attention to this. The big thing they do here is they do regular quality assessment scans. So pretty much almost every day on every scanner, they put in one of these oil phantoms, they take some basic parameters, they save that raw data, and they automatically correct these time series, which show, temporal signal noise changes over time. Oh, look, something funny happened here. Let's go check what's happening. Is it just a one-off thing, or was there an issue from the scanner? And you can, by doing these daily QA scans and looking at them rapidly, when something goes bad on the scanner, the sooner you know, the sooner you can correct it. And the number of times I've heard stories of, oh yeah, 5 of our receiver coils on our 32-channel coil died 6 months ago and we just noticed it. Well, there goes those 6 months of data. So keeping track of this stuff is huge. There's more and more software to sort of keep track of it. So this is a package, fMRI QC, which helps automate some of these stability measures. And then just for any user, monitoring your results in real time can save you a lot of headaches, because that lets you, if you have a subject that you can correct on the fly, you can say, oh, we got to collect that scan again. If it's something you can't correct on the fly, you can say, okay, there's an issue. We got to speak to someone and figure out what's going on. So like these are, you can see as this time series goes on, they move their head here. So this is the motion trace, and this is the fMRI signal trace. So there was this big motion that ended up in the data. This is a subject that you might say, maybe you shouldn't move your head like this during the scanner. And maybe you have a chance during that day to sort of correct it before you lose that scan, particularly if it's a patient. There's also built into AFNI, which is one of the software uses, this function called instant correlation, Instacore, which lets you just put down a seed voxel and correlate to the rest of the brain there. So here we could see that in the subject, we're getting these really big correlations between vessels, and maybe there's some sort of artifact going on here. So, on your real-time scans, if you play with this Instacore function a bit, you could potentially quickly identify there's something weird going on, and maybe even correct it on the fly. That's another example of artifacts we could see. And that's about it. In summary, there's always going to be noise sources in fMRI. The more you understand about noise sources and what decisions affect them, the better you can control and correct for them post-processing. So hopefully I've given everyone sort of a sense of what to think about when you're thinking about noise and acquisition, so that you at least can sort of ask the right questions if the need arises. And I'll acknowledge getting a bunch of slides or advice from people. Particularly on the acquisition section, I use a lot of Ranchas Huber's examples because he's 2 seats away from me, and it's much better to highlight the work of someone next to me than some random papers on the internet. And the work's awesome. Okay. Any questions? Okay.